Motion planning for variable topology trusses, reconfiguration and locomotion. This work is done by Chao Liu, Sencheng Yu and Mark Yim. A variable topology truss, or VTT, is a modular robot in truss structure. Each module contains a spiral zipper prismatic actuator and a mechanism to attaching the ends at truss nodes. The node enables linkages to remain connected during the motion, and the geometry shape of a truss can be changed by moving nodes around. Furthermore, two nodes can be linked in an open chain to do topological reconfiguration. Two separate nodes can merge into an individual one. In addition, a single node can be split into two. A spiral zipper actuator has a high extension ratio. This enables the large workspace and reconfigurability of the robot. For a VTT, the configuration space of a node is complicated due to the complexity of the obstacle region. The obstacle region is formed by multiple polygons, and here we show all the obstacle polygons computed for node V0. A fast algorithm to compute the boundary of the enclosed free space has been presented in our previous work. For real robot applications, we need to consider the physical size of the elements. We grow the obstacle region by converting every obstacle polygon into an obstacle polyhedron, since the truss members have non-zero thickness. Then we can get a new free space boundary for the same node. We extend this work to compute the free space for a group of nodes. The singularity avoidance condition can also be modeled as a plane that can be added to the obstacle region. The sampling space is significantly decreased and collision check greatly simplified so that RRT framework can be applied efficiently. An efficient collision model can be applied. We just need to check the intersection between any still member with the triangle generated from the moving member. Or compute the local obstacle region for a group of nodes and check the collision. For motion planning, in addition to the member-to-member collision avoidance requirement that is the most significant issue and can be solved by the configuration space, we also need to make sure the angle between connected members remains above a certain value because of the mechanical components at nodes. The length of every member has to be within a valid range. The truss should remain statically stable under gravity and also maintain enough manipulability. With this framework, we can do the geometry reconfiguration planning very quickly. Here we show a scenario that is to reconfigure a truss from a cubic shape into a tower. The average planning time consumed for 1,000 trials is around 4.2 seconds with the standard deviation of around 2.0 seconds, and the success rate is 100%. In these trials, the maximum planning time is around 7.5 seconds and the minimum is around 1 second. And this approach is much more efficient than previous approaches. The next part is the topology reconfiguration. The free space of a node is usually partitioned into multiple enclosed subspaces. If the node needs to go from one subspace to another one, then topology reconfiguration is required. We present a fast algorithm to search all enclosed subspaces in the free space of a node. For example, if the node V0 needs to go from its initial position to a position inside this pyramid subspace, we need to split the node in order to overcome the internal obstacle. Topology reconfiguration actions are highly affected by the node position, and a routine is created to generate as many samples to span the enclosed subspace along with valid topology actions as possible. Two transition models are built to connect two adjacent enclosed subspaces, and a graph search algorithm can be applied to compute a sequence of topology reconfiguration actions efficiently. Here we show a test result by using our topology reconfiguration planning. We first verify topology reconfiguration is needed if we want to move node V5 from the position in the yellow space to a new position inside the green space because these two spaces are separated, and then find the right way to split the node so that the enclosed free subspaces for both newly generated nodes can contain the goal position. After splitting this node, we can use the previous geometry reconfiguration planner to plan the motion of these two newly generated nodes efficiently. The total average planning time for 1,000 trials is around 22 seconds with the standard deviation of around 0.7 seconds, and the success rate is 100%, including the enclosed subspace computation. the Topology Reconfiguration Planning, and the two-node Geometry Reconfiguration Planning. In these trials, the maximum planning time is 24.4 seconds and the minimum is 24.0 seconds. This next example is a more difficult motion task which involves more topology reconfiguration actions. The task is to move the node from its initial position that is in the center of the truss to a position outside the truss. The node is currently inside the yellow space, while the goal is inside the blue space. Topology reconfiguration is needed. In order to finish this task, we have to first move the node outside the truss and split it into two, navigate both of them to the green space, and merge them there. If splitting the node inside the truss, one node has to traverse a region leading to singular configurations. After merging these two nodes inside the green space, split the node in another way so that they can be moved and merged inside the blue space and moved to the goal position. With 1,000 trials, the average planning time is about 86.5 seconds with a standard deviation being around 2 seconds, and the success rate is 95.9%. In these trials, the maximum planning time is around 92.9 seconds and the minimum is around 80 seconds. VTT locomotion planning can also be handled by solving a geometry reconfiguration planning problem. A single locomotion step is equivalent to rotating the truss along a supporting edge by some angle so as to change the support polygon. We can compute the goal positions for the involved nodes and the planner can automatically generate an intermediate state due to the truss stability requirement. Our planner can be applied to an arbitrary truss. Here is an example to execute a rolling locomotion step using a truss. We first move two nodes to expand the support polygon, then move another two nodes so the center of mass enters the new support triangle. Finally, we move the last node to the center of the truss. With 1,000 trials, the average planning time is around 8.3 seconds with a standard deviation being around 5.9 seconds, and the success rate is 100%. In these trials, the maximum planning time is around 24.5 seconds and the minimum is around 0.5 second. This performance is much better than previous approaches. A VTT can follow a trajectory of support polygons to navigate in an environment and the planner can do the locomotion planning in real time because of its efficiency. This work is funded by AFOSR.